Now we want to try and go in the opposite direction. So now we want to take logarithmic equations and rewrite them in exponential form. So remember, we want to get them in the form where they have a base raised to an exponent equals the argument. I'm just going to rewrite this first one because I like to have the log on the left-hand side and what it's equal to on the right-hand side. So that then I can follow the process of start at the base, raise it to the exponent, and set it equal to the argument. So this log in exponential form would be 3 raised to the power of t equals 8. If I keep following that process of I start with the base, raise it to the exponent, set it equal to the argument, I'll get 5 squared equals 25. Start at the base, raise it to the exponent, set it equal to the argument. So 6 to the first equals 6. No base implies a base of 10, right? Our common log. So base raised to the exponent equals the argument. So 10 to the negative 2 equals 0.01. Base raised to the exponent equals the argument. So c raised to the 17th power equals m. And finally, base raised to the exponent equals the argument. So e to the negative 0.0111 equals 0.989. Why do we care about being able to do this? Because if we can write logarithmic equations in exponential form, it allows us to solve for the variable. So if I rewrite the following in exponential form, then 3 to the power of 0 equals x. So 3 to the 0 power equals x, and anything to the power of 0 is 1. In the next case, I have 5 raised to the power of x equals 25. So 5 to the x power equals 25. And if I rewrite those with the same base of 5, 25 is 5 squared. When I set the exponents equal, I find that x equals 2. Again, base raised to the power equals 64. So x to the third equals 64. If I raise both sides to the 1/3 power to get the exponent on the left-hand side to be equal to 1, I get x is equal to the cube root of 64. And the cube root of 64 is 4. If we keep going, x to the first power equals 8. So x to the first power equals 8. So x is equal to 8. 3 raised to the power of negative 2 equals x. So 3 to the negative 2 equals x. To get a positive exponent, I'll move that to the denominator. So I have 1 over 3 squared equals x. And x is equal to 1/9. And finally, 32 raised to the 2/3 equals x. So I have x is equal to the cube root of 32 squared. Now 32 isn't a perfect cube, but there are perfect cube factors in 32. So we're going to break this down into the cube root of 8 and the cube root of 4 still squared. The cube root of 8 is 2. We'll keep the cube root of 4 and keep it squared. And now remember, each piece will have to be squared. So x is equal to 2 squared, which is 4. And the cube root of 4 squared is the cube root of 16. And again, 16 is not a perfect cube, but it does have perfect cube factors. So we'll break it down into the cube root of 8 and the cube root of 2. And the cube root of 8 is 2, keeping the cube root of 2. Finally, we get x equals 8 times the cube root of 2. We've also learned how to evaluate logs given specific values and then using our properties of logs. So if I want to find the log of 25 over 6, I can rewrite in terms of log 3, log 5, and log 6 because those are the specific examples I know. So I can rewrite 25 as 5 squared. And then my properties for logs, if I am dividing in the argument, then I can separate that into 2 logs that are subtracted. So I'll have log of 5 squared minus log of 6. And the rule for if we have an exponent in the argument, that can come out front. So it'll be 2 log 5 minus log 6. And now I can plug in the values that I'm given. So 2 times 0.699 minus 0.778. And when I evaluate that, I get 0.62. For log 50, I can break that down into its factors of 5 times 10. And the rule for multiplication in the argument is I can separate it into 2 logs that are added together. Now log 5 I was given, log 10 is one of those that we should just know because it means log base 10 of 10 equals what? Right? So 10 to what power equals 10? And that power is 1. So log of 10 is equal to 1, and log of 5 we were given. So I can say 0.699 plus 1 is equal to 1.699, which is the value of log 50. We also learned how to condense logarithms into a single logarithmic expression. We want to always take care of the numbers out front first, so they can be pulled up into exponential position. So this would become log of x to the 4th plus log of y to the 3rd. And the rule for adding logs to condense it into one single logarithm is to multiply. So we have log of x to the 4th times y to the 3rd. Again, we're going to pull the numbers out front up into exponential position. So it'll be log base a of x to the 1/2 plus log base a of y to the 3rd minus log base a of x squared. And our rule for addition is to multiply the arguments, and our rule for subtraction is to divide. So we'll have log base a of x to the 1/2 y to the 3rd, because they're added, which means multiply, and then over x squared, because it's subtracted, which means divide. And then we just want to follow our rules of exponents to simplify the x values. So if I have a 1/2 x on the top and 2 x's on the bottom, I can subtract a 1/2 from 2, which gives me 1.5 or 3/2, and I'll leave that in the denominator because it has the larger exponent. And the last thing we're going to do is expand logarithmic expressions, meaning we're going to take anything within the argument that's in the numerator or multiplied together and separate those into individual logarithms that are added together, and take anything that's in the denominator, which implies division, and change it into a single logarithm that is subtracted from the rest. So in this case, I would have log base A of x squared, because it's in the numerator, minus log base A of y cubed, because it's in the denominator, minus log base A of z, because it's also in the denominator. And then I'm just going to pull all those exponents out front where necessary. So this would be 2 log base A of x minus 3 log base A of y minus log base A of z in expanded form. And for the last one, we'll want to rewrite as a power of 1/3 instead of the cube root of the argument, so it'll make it easier for us to expand. So we'll have log base c of x to the 6th y to the 3rd over a squared z to the 5th, all raised to the 1/3 power. And then we want to make sure we raise everything within the argument to the 1/3 power. So we'll get log base c of x squared y over a to the 2/3 z to the 5/3. And now we can go back and do the same thing we did in the last problem. Anything that's in the numerator and multiplied, we can separate into individual logs that are added together, and anything in the denominator implies division, so it can be subtracted off as its own individual log. So this becomes log base c of x squared plus log base c of y minus log base c of a to the 2/3 minus log base c of z to the 5/3. And then I'll just pull all of these exponents out front as necessary. And this will become 2 log base c of x plus log c of y minus 2/3 log base c of a minus 5/3 of log base c of z. And that will be your answer in expanded form.